Assalamu alaikum. Hi everyone. In this video, I will demonstrate how to write a Matlab program to perform the so-called system identification using the linear regression techniques. So in this example, I will show how to identify the parameters of a first-order low-pass filter using the linear regression. By the way, in order to identify a system, we require at least two information. So number one is the structure of the system transfer function. Like in this particular problem, the transfer function has constant numerator, and its denominator is defined as a first order polynomial. And then the second information that we need to have is a set of input-output data that is normally acquired from an experiment. So this can be done by applying numerous input excitations to the system by varying a certain variable, like in this particular example, the input frequency is varied. Then the corresponding output response is observed. Okay, now let's get into the problem. So the structure of the transfer function for this RC filter is given like this, okay, in which there are two unknown constants, A and B, a number of input voltages with the same amplitude but with different frequencies are applied to the circuit. Then the amplitude and the phase shift of the output voltages are observed. Notice that since the phase angle of the input is 0, then the phase angle of the output is already the phase difference between the output and the input. Next, we need to process this data to present it in the form of transfer function. So we know that if a transfer function is presented in the polar form of complex number, its magnitude equals to the gain of the system, and its angle equals to the phase of the system. In other words, we need to process the data, to obtain the gain, and by combining the gain with the phase difference, we will be able to generate the data for the transfer function as the complex numbers. Okay, and another important step before applying the linear regression is to linearize the equation. And sometimes some variable transformation is required during the process. So in this particular problem, the transfer function can be rewritten like this, and then by introducing a variable y, which is equals to 1 over h, we get a linear relationship between this new variable y with the frequency. So now we rename the frequency with variable x, and then we get this relationship y equals to mx plus c. So by identifying the constants m and c, we can subsequently defining the unknown constant a and b using this relationship. All right, now let's begin with the Matlab programming. So suppose that we already have the raw data in Excel format like this. Okay, so this data is actually the same with the one that we have on the slide. All right, so they are the same value. And then if this Excel file is already included in the Matlab current folder, we can simply import all these values to the Matlab workspace. Okay, so let's begin with the new script. All right, so let's begin the first line with clear and CLC. And then we wish to import the values from the Excel file to the Matlab. So that can be done by writing by using the Excel read command, and then we specify the file name, which is the rc filter.xlsx. Okay, then we know that the first column of this data is the frequency, followed by the input voltage amplitude, and then output voltage amplitude, and the rightmost column, which is column number 4, corresponds to the phase angle. So we can write something like F, which is frequency, equals to the first column of the data, the input voltage amplitude is the second column of data, then the out, which is the output voltage amplitude, is the third column, and finally the phase angle is the fourth column of the data. Okay, if we run everything up to this line, okay, let's name this file as id rc filter. Okay, we should be able to see all the quantities appear in the workspace. So now data is a matrix 6 by 4, and then each of the quantities f, phase, v in, and v out becomes vector with a length 6 by 1. Okay, and then if you want to check the elements of one of them, let's say f, you just type f and hit enter in the command window, and you manage to see all the elements of the vector. So next, we need to specify the length of the vector. Of course, it has 6 elements, but more systematic, by using more systematic way, we can write something like n, big N equals to the length of f. Okay, and then let's refer to the slide. We wish to have the transfer function in the form of complex number, or more specifically the exponential form of complex number, in which the first term is actually the magnitude of the transfer function, which equals to the gain, and then times the exponential power j theta. So theta in this case is actually the phase angle, exactly equals to this one. But in order to process the angular value in Matlab, we normally prefer to use radian instead of degree. So now let's specify the magnitude of the transfer function as h underscore mag, which means magnitude of h, and then we can write v out divided by v in. By the way, we have to be careful. Instead of just writing this division operator, we have to put a dot before it, because this is actually the elements wise operation, meaning that the first element of v out divide by the first element of V in, the second element of V out, divide by the second element of V in, and so on. So it is actually rather the elements wise operation. So we continue, and then the phase angle of the transfer function, so let's call it h underscore phase, equals to the phase angle that we have here, but we wish to convert it into radians, so we times with pi and divide with 180. And then finally we can construct this transfer function in this exponential form. So we can write h equals to h mag times, again we need to use element-wise operator. This time the element-wise multiplication times the exponential power j theta. So we can write 1j times the phase of the transfer function h underscore phase. All right, so next continue with the remember that we need to rearrange the transfer functions such that it appear in the as a linear equation, and then we rename 1 over h with another variable which is y, and then we get a relationship y equals to mx plus c, in which x is actually the frequency itself. So we can continue with y equals to 1, okay, element wise again, element wise division divided by h, and then x is the frequency. All right, then we can continue further with the linear regression algorithm. So we need this quantity x squared and then x times y. So let's name x squared with x as q maybe. So again, the elements wise power 2, and x times y, let's call it x tmy, you know, stand for x times y, equals to the element wise multiplication between x and y. All right, so continue with the slide. So then if we have all this expression in this matrix form, which is n and then the summation of x and then summation of x again, and then the summation of the x squared on the left hand side, and then on the right hand side we have a matrix with elements the sum of y and the sum of x times y. So we can find the constant c and m, you know. One of the way is by simply bring this matrix to the right hand side, and then we get like Cm equals to this matrix, the inverse of this matrix times the matrix on the right hand side. So let's call this the big A and this one as the big B. Okay, then we can have something like, we can write big A is matrix, the element is n sigma x, so n sum of x, so next line sum of x, then sum of x squared. Okay, so we accomplish matrix A. Maybe we can remove the semicolon first to display the value on the command window. B is the sum of y, followed by the next line is the sum of x times y. So sum y and sum of x times y. Okay, let's check the command window and run up to this line. So we can see that the matrix A is a 2 by 2 matrix and matrix B is 2 by 1 matrix. So if we write something like inverse A times B, so the first element of the answer is actually constant C and the second element is actually the constant M. But if you want to follow the method of finding C and M, as shown in this on the slide, by using the Cramer's rule, you can also do something like, so this is called the determinant. So you can write C equals to the determinant of, okay, notice that the first column of this is actually matrix B, and the second column is actually the second column of matrix A. And for M, the first column of this is actually the first column of matrix A, and the second column of this term is matrix B. And for the denominator, they are both of the denominator for C and M are actually the determinants of matrix A. So you can see that exactly this, all the elements of A appear at the denominator of these expressions. So if you want to use Cramer's rule, you can write C equals to determinant, and then round bracket, and then put square bracket. So we want to build this matrix. So begin with the matrix B, and then the next column is the second column of matrix A. So we divide with the determinant of matrix A. Okay. And we can copy this and modify it to have the expression for M, so this becomes the first column of A followed by B and then divide with determinant A. Okay, so either inverse A times B or this manner, they should provide the same answer. Okay, so I run this and then I get the results. And finally, we can find the unknown constants for the transfer function, which are A and B, using this relationship. So we can finally write A equals to J2 pi over M, or in Matlab, we should write 2J times pi divided by M, and B equals to A times C. Okay, so run everything. So finally, we get the constant A equals to, a large number like this, and constant B equals to this one. So if you inspect the value of A and B, you will notice that the imaginary part for A and even for B are relatively smaller than the real part. Theoretically, A and B should be a real should be real numbers, because they actually becomes the coefficients for, it's not coefficients, like a parameter for this transfer function. All right. Additionally, if you want to display this table, the values that corresponds to the linear regression, if you want to visualize this in Matlab, you can do that using fprintf command, but this is actually not necessary to compute all the constants C, M, A, and B. But if we can, visualize these values, that might be helpful to give more understanding on the process of linear regressions. So maybe we can put the table, just before we define the matrix A and B. Okay, so we can write for I equals to 1 until n. So there are how many columns that we need to have? 1, 2, 3, 4. But remember that since y and x times y are complex number, it becomes a little bit more complicated. So we can write f f prints f. Okay, then put some inverted commas. So first we have to specify the first column, which is xi, and then followed by xi squared, which is x squared I, and then the real part of yi, and then the imaginary part of yi. Okay, and then followed by the real part and the imaginary part of x times y. Real, so let's maximize this first. The real part of x times y I, and the imaginary part of x times y I. Okay, it's quite a tedious work, but you know, it is not necessary to compute. Again, it's not necessary to compute all these constants, but we wish to visualize this table in the command window. Okay, so now we have 1, 2, 3, 4, 5, 6 columns. So x is the frequency, which are round number. So this one will be number with, let's check this slide. You know, we call this as exponent, you know, times 10 power something. Okay. Okay, so we can specify x with the, you know, round number. So we use format D, you know, with like 6 space, and then x squared maybe yeah, so let's use exponential format, you know, times 10 power something, and then the the real and imaginary parts for y, so they are like floating numbers, so let's use the floating number format, 6.4 maybe f. So this is for the real part, and then plus the imaginary part, I'm not sure, I think 5 digit is enough for that, 0.4 f. And then let's put j to indicate this is the imaginary part. And then how about the x times y? I think we can use this format as well and paste it here. And don't forget to put the enter. Okay, let's check the command window. What do we have if we run these lines? Okay, so we can see that the first column is actually x and then x squared. This is y, and this is x times y. Maybe we need to put some header to indicate this. So let's copy this and paste it here. Okay, so change this to string. So let's just write x, you know, this is just the header for the table. You can write literally anything, so it does not give any error. So x squared, so what this is, y, just write inverted comma y, and then this is x times y, x times y. Okay, let's specify the space or the digit for each of them. So change this to string, and this one is also string. Let's give 6 digit or 6 spaces, and then how about this? We combine this, maybe 8, and then finally this one, maybe 8 again. You know, we can always change this if we think that the presentation is not very good. Okay, run again and then check the data. Yeah, so put some, maybe 16 maybe. Okay, run again. So hopefully the header is, now it is aligned nicely. So again, this table is not necessary to compute all the constants, but it's better to have it. And secondly, maybe we want to do something like graphical validation, to verify that the constants A and B can produce the transfer function that fits with our actual data or the measured data. Okay, so let's do some plot down here. So since this is like the transfer function plotting, it's normally use the log scale. Okay, so I think we can put some comment here, A and B, and let's continue down here to plot some graph. Okay, first we have to create the array for the frequency, which will become the horizontal axis for the plot. So we write something like ff. Now it become the array for the plotting purpose. So we define it as log space. Starting from let's check the slide. So f will vary from 0 to 10,000. So this is like 10 power 4. So let's make it as 6 maybe. So we use 100 step size for the frequency array. Okay, and then the computed transfer function, now we use the value that we acquire here, A and B. So equals to A, okay, divide by, refer to the transfer function in the problem, A divided by j 2 pi f, so 2j times pi times ff plus b. Okay, and then the magnitude of the computed transfer function, let's call it as h mag equals to the absolute value, abs of the computed transfer function, and the phase of the computed transfer function equals to the angle of the computed transfer function. Okay, now we can begin with the plotting. So we wish to have like the plot for the magnitude and then followed by the plot for the phase. Okay, so we can use subplot. So subplot with 2 by 1 formation. Okay, so the first graph will be the plot for the magnitude. So let's use the full log scale, log, and then ff comma with the magnitude. Magnitude. Okay, and then what we can have the second plot, which is the angle. So again, subplot 2 by 1, the second graph. This time we want to use semi-log because we want to preserve the vertical axis with the radian, instead of log. So use semi-log, in which semi-log x means we only use the log scale for the horizontal axis. Okay, so ff comma the angle of the computed transfer function, sorry, phase. Okay. All right, so let's run this and see and check what do we have. Okay, it's require a little bit of time. So now this is like a board plot. You can call it board plot of the computed transfer function. Okay, and then we want to plot the measured value, you know, like the one that we have in this table on the same axis with the computed value. So this can be done by adding some lines down here. So first we write hold on, and then using this, let's copy this line, paste it down here. So now this is actually the value that comes from the raw data. So we call that just now as the HMAC, and then let's put some marker, you know, with maybe red color. R stand for red, and then use the asterisk to show the location of the points, and then we continue this with hold off, and also using this similar manner we can write hold on after the semi-log plot for the phase. Okay, and then plot the phase, the measured phase angle, you know, these angles versus the frequency. Okay, we also can use the red asterisk as the marker, and then we write hold off. Okay, if we rerun everything again, so hopefully this graph can show the location of the points of the measured value is kind of have the agreement with the slope or the curve of the computed values. And if you like to add some label, you know, for the axis and also the legend, you can add some lines here, x label, the frequency f, you know, so you can write anything because this is just the label, the string, and then you can write y label is the magnitude of h. So maybe this, you know, this notation, and then you can put some legend, you know, like the blue line is, let's label it as the fitted graph, and then the red asterisk is the measured value. Okay, so we can also copy this and paste it down here. So we change this to the angle, or maybe we can write theta, so in radian. Okay, let's rerun everything again, and we should get a better graph. So this is the graph, you know, with the labels on the horizontal axis and vertical axis. So now we already put some legend, you know, to indicate that the blue lines is the graph or the response for the transfer function that we compute using the linear regression, and the red marker is actually the values from the measured or the raw data that are acquired from the experiments. Okay, so I think that's all for now. Thanks for watching.